Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we are going to continue to discuss bolted connection failures and bolted connection design for timber connections. And previous videos, we talked about two of the potential failure modes, one being yielding, the other one being row shear. And in this video, we're going to start by talking about group tear-out failure modes. So this is something that if you've done steel design will also be familiar to you, because in steel design, we design for these group tear-out failure modes. So you can imagine, row shear is pretty easy to imagine. You could also imagine that as I pull on a piece of wood, if I have, a group of bolts in this piece of wood, I have bolts, here, 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 then you could imagine that instead of pulling out two strips of wood, they could pull out like a whole chunk of the piece of wood. Now, in order to do that in wood is a little bit more difficult than in steel, because to pull out the chunk, I have to fail both in shear, but also I have to fail in tension. And you remember that for wood in tension, it's quite a bit stronger than wood in shear. So for a group pullout failure mode to happen, we basically have to have pretty short rows, and the bolts probably have to be pretty close together in the cross-section dimension, so that I have a relatively small tension piece that I need to fail. Okay, so it looks something like this. So instead of pulling out two plugs, which are plug rows, I pull out basically the entire member. So you not the entire member, I pull out a big chunk of wood material from the center. And you have to imagine, for these failure modes to exist, all the bolts have to move together. So I have to move all four bolts at the same time. They all have to move, and they have to pull out a chunk of wood with them. Okay, so in this case, instead of having two shear planes per row for row shear, I don't have rows anymore. I just have one big chunk. And that chunk has only one shear plane on each side. Okay, so it still has two shear planes. So I have a shear plane over here and I have a shear plane over here. But in addition to that, I have basically a tension failure. Let me draw that in a bit of a better place. So I have to fail two basically shear planes plus one tension plane, and that one tension plane, per unit length is going to be significantly stronger than the shear planes, because the shear planes are basically, we're failing the lignin. We talked about this with the straws. So if I'm shearing like this, it's relatively easy, but to actually fail a part of that in tension, so even if I just take a few of the straws in the middle and try to fail that in tension, I basically have to rupture the straws. So it's quite a bit stronger in that direction. Okay, so unlike row shear, I can't get this in both directions. So if I have my group tear out and I'm pulling on this member, so the bolts want to pull out the bottom, that's a way that I can get group tear out. But if I'm pushing on this and the bolts are pushing into the middle, then I can't have a group tear out. So, critical to the failure of tear out is that I need to be able to tear a piece out. I didn't need that in row shear. In row shear, I could fail those shear planes and have that in combination with a small embedment failure at the end of one of the bolts. Okay, but I can't get that in group tear out. I can't tear out a chunk into the piece of wood. So I only have to worry about this failure mode if I have loads that are parallel to grain and that they are basically pulling towards a loaded end. Okay, so how do we determine what is the strength for group tear out? Let's look at the mechanics of this situation. Okay, so if I want to pull this chunk out, okay, oh, I missed one of the bolts. If I want to pull this chunk out, all the bolts have to go down, and they all have to go out of the piece of wood and take a chunk with them. So I'm going to have to cut out a piece that looks something like this. Okay, so what about the shear side of that? Okay, so if I look at, if I look at just the edge here, Okay, if I'm just looking at the shear part of that, we can notice that the shear plane is similar to what it looked like when we had our row shear. So let me make this one solid, because this is the part that's actually breaking. Okay, so if I'm only interested in the right line there, the right orange line, and I need to find the shear resistance of that line, we already looked at how to calculate shear resistance of shear planes when we looked at row shear resistance. Now, if you look at this specific case, along that line, we only have to shear one side of the bolts, not both. So for row shear, we needed the green line and the orange line to pull out the plug. But here, we're pulling out the whole center of this, so we don't need to shear the green line anymore. So basically the shear resistance of that orange vertical line is just half of what the row shear resistance would be for that row. So we already have a calculation method to find the row shear resistance. So if I take half of that, then I'm going to have basically the shear resistance of just that one-sided shear plane. Okay, what if I look at the this bit now? Okay, so the side shear planes we just talked about. What about this bit that's in the middle? So we're talking about basically I need to fail these thick orange lines in net tension failure, basically. So what I'm going to do basically is I'm going to need to calculate the length of those lines. So if I go from center to center, this would be basically, in this particular case, this would be 2 times my SC, which is my column spacing, or SQ if I'm talking about 08619, which is the perpendicular to grain spacing. Okay, so I have basically, in this case, 2 individual bolt spacings, right? One between here and here, and one between here and here, right? So those are my 2 bolt spacings. That's why it's 2 times. Okay, now if I want to find the length of just the orange lines, then I have to remove the bolt holes, okay, because this is a net tension. This is a net tension, not gross. And so we're going to find the net area for PG means for group tear out. So for load, P is load, compression, or tension. G is for group tear out. I is for this particular member. Then it's going to be 2 times SC. Okay, I'm just going to use SC for now. It could be SQ, which is the total length. And then I'm going to subtract half a hole on the left minus the full hole in the middle minus another half hole on the right. And I'm going to multiply all of that, of course, by the thickness T to get the area of those planes. And so I get basically 2 SC minus 2 times hole diameter times T. And we have to remember that the hole diameter is bigger than the bolt diameter, and we usually assume it's bigger by 2 millimeters. Okay, so then what's the resistance in tension? Tension resistance, we would expect to look something like FT times APGI. So FT would be our strength in terms of stress, and APGI would be the cross-sectional area. We've done net area before. Of course, we're also going to have some phi factor on there in general. Okay, so then the last bit that I want to point out is with regard to shear resistance. Let's remember how we talked about row shear resistance before, because we're going to need the row shear resistance for here. Okay, so when we had row shear resistance, we called those PR. That's for, tension compression. R is for row shear. And we called that IJ. So this one, we could call that PRI NR, okay, where NR, so where PNIR, PRI, remember I, NR for row NR. So if we had 3 rows, we have row 1, we have row 2, we have row 3, we have 3 rows, so NR is 3. So PRINR is PRI3. It's just the last row. Okay, where NR is just the number of rows, so NR is the last row. Okay, and then the one at the beginning is PRI1, where 1 basically means it's the first row. Why do we need these? Because basically when we do row shear, this one is the first row, and this one is the last row. So we're going to need the row shear for the first row and the row shear for the last row. And remember, we're going to need only half of each of those. Okay, so if I wanted to add up what's the total shear resistance that is inside this group tear out mode, where I have half a row shear on the left and half a row shear on the right, then that is going to be half of PRI1 plus half of PRINR, where NR is the last row. And if I group those together, I will find something like PRI1 plus PRINR and divided by 2. So it's basically the average of the two row shears. And the reason that I'm pointing this out is because we find this exactly in the equation for group tear out. And that's where it comes from. Okay, so now let's go through the full group tear out resistance calculation procedure. Okay, so just like row shear, I'm only calculating at one time the resistance of one side of the connection. So I have my left side, my right side, these are connected together. Sorry, I should do it opposite because of the flip. I have my left side and my right side. These two are joined together. And so I'm going to calculate group tear out for the left side using this approach. And then after I'm done the entire approach, I can come back and find row shear, group tear out for the right side, this side here, failing. And that's if both of my sides are wood. If one of my sides is steel, then I'm going to use the steel code to the steel standard to calculate the group tear out there. Okay, which we're not going to do in this course. So for one side of the connection, I have to do this for each member. I have to calculate the group tear out, and then later I'm going to add up all the members on that side to find the total group tear out resistance for that side of the connection. So just to remind ourselves is what we're talking about. So if I have a 3-member connection, I have 2 members on the left side and 1 member on the right side. So I'm going to find group tear out for this member first, then this member, then I'm going to add those together, and that will give me the group tear out resistance for the left side of the equation. That's the approach. Okay, so let's go back and talk about how to actually do it. So, so for each member, I'm going to calculate group tear out resistance, and this is the equation to do it. Okay, so that's the overall equation. Okay, this first part here is obviously the shear planes strength, and that PRI1 plus PRINR divided by 2 is just what we talked about here. So it's half the row shear of the first row, half the row shear of the nth row, like the final row. And so that's how we get that. And then this bit here is our net tension, right? Where APGI is our net area between the first and the last rows, taking into account, of course, the bolt holes. So it's basically the area across those thick orange lines right there, as we already talked about. Okay, so it totally makes sense. Now here we have KD, KS, TKT on the right for the net tension, but how come we don't have it on the left? That's because PRI1 and PRINR, which we learned about when we calculated row shear, already includes KD, KS, VKT. So it's already built into the PR values that we use there. So we don't include it again twice. Okay, we have to be careful that PRI1 and PRINR have to be in newtons if we want this equation to work out in terms of units. So that's very important. Otherwise, you're going to mix units, right? Because FT is an MPa, APGI is going to be in millimeters squared, so MPa times millimeters squared is going to be in newtons. So then to add this, which is going to be in newtons, to this, the one on the left has to be in newtons as well. So that's a tripping point that a lot of people will run into when using this equation if they're not careful. Okay, FT is our tension strength of wood, which we get from our regular tables. Okay, and APGI, as we said, is just the critical perpendicular net area between the first and the last rows. So it's basically the area between the bolt holes, between those first and last rows. Okay, so then that gives me PR, that's row shear strength for I, row shear resistance, PRR, row shear resistance for member I, PRRI. And then if I have multiple members on that side of the connection, like if I have a 3-member connection, then I have to add them all up. If I don't, then the addition is trivially easy because I just add one element. Okay, so PGRT, group tear out strength, group tear out, PG, R for resistance, T for total. So for all the members on that side of the connection is the sum of the PGRI, the group tear out resistance for each member I. So if I only have one member, then PGRT just equals PGRI for that only single member. And that's it. That's how you calculate your group tear out resistance. Okay, so the next one is a pretty quick one because we've basically done it before, which is net tension failure. Okay, so net tension, which we've looked at before, we've done net tension strength before, is just basically cutting off the entire cross-section of the piece at the minimum net section failure location. So that will be the furthest bolt, basically. Can I have net tension failure here in the second line? No, because then only half of the bolts would be coming off the bottom of the connection. Remember, whatever failure I have in my connection, all the bolts have to separate off of the main body of the connection. So in this case, this whole part here comes off. It's not a plug anymore. It's just I basically pulled off the bottom of the connection. So this is pretty tricky to do, as you can imagine, because I have a lot of tension failure, and tension is much stronger than shear failure in wood, as we've talked about before. But if I cut out enough of my piece of wood and maybe my the bottom of my connection is long enough that it's very difficult to fail in row shear, or I have a lot of bolts, I have a really long row shear connection to fail, then I could definitely get net tension failure. Okay, so we can basically skip directly to how to calculate this because, as I said, we've done it before. So just like row shear and group tear out, we're still dealing with just one side of the connection at a time. And if we have multiple members on each side of the connection, then we find the net area for each of those members, and then we're going to add them together in the second step. But in order to actually do the net tension calculation, it's very easy because we've done it before. We just use the net area calculation from clauses 6.5.9 or 7.5.11. So one is for, remember, lumber timber, the other one is for glulam. So that that calculation we've covered before, and basically it's just FT or FTN for glulam multiplied by the net area multiplied by a material reduction factor. So that's very easy. So I just set my T NRI for that. One thing that we need to remember is that the net area is the gross area minus the bolt holes. So just like before, so I'm going to put a note up here about that. Okay, so I have to remember to take out the bolt holes, and I have to remember that the bolt holes are bigger than the bolts by about 2 millimeters. And also that we have a limit on our net area, which we've seen multiple times. And we talked about this very early on, that my net area has to be greater than or equal to 75% of my gross area. So I can only cut out at most 25%. Okay, so then once I find my tension strength, my net tension strength in the connection for each member on that side of the connection, then I find the total resistance. And that gives us TNRT, which is my net tension strength total, which is the net tension strength of all the members on that side of the connection together. So if I have a 3-member connection, the one that we looked at before, on my left side, I had 2 members. On that side of the connection, I'm going to add up the net tension strength for both. If the net tension strength is the same, I'm just going to multiply it by 2 and calculate it once. Okay, so I'm going to put one last cut in here. This video, we looked at gross tear out, and then we looked at net tension, and sorry, group tear out, not gross tear out. And then in the next video, we are going to finish up bolted connections by looking at the splitting failure mode, which is the one that's perpendicular to grain, and also how we sum it all up to get a summary of all the bolted connection requirements, and how we deal with if I have a combination of splitting and parallel to grain failure modes like net tension and group pullout.